Hi, in this week's lab, we're going to talk about planes, geologic planes, so surfaces, planar surfaces, and how we measure them and how we record them on paper. So I've just showing a picture from the internet of a typical rock outcrop. So these are sedimentary rocks. There's some pine trees for scale, some kind of dry creek bed. You can see that the layers are the geologic layers here are tilted. This is pretty common. Sedimentary rocks originate, they start out horizontal, roughly horizontal, and then due to different processes, geologic processes, they tend to get tilted. They get pushed up and or pushed down and folded. Interestingly, here you can see like a layer, the present day horizontal is kind of just some alluvium dirt sitting on top. But underneath these rocks are tilted. So we want to be able to um, sort of describe this in a consistent, efficient way when we encounter rocks. And so to do that, we're going to use something called the strike and the dip. Okay, so imagine a some dipping rock layer. And let's draw this in 3D. Imagine there's a sort of imaginary horizontal surface. This surface would cut through. Um, okay, so let's label this imaginary horizontal surface. Okay, so we're going to define um, two things. The strike, these two things will give us a complete description of any plane that's tilted. So the strike is the direction taken by a horizontal, actually by a structural surface. For example, a fault plane or bedding. Bedding being the um, sedimentary, original sedimentary layering. As it intersects the horizontal. So if we could, so that intersection, I'll use a different color here. Like the direction of this green line I'm drawing. So if we could, you know, take a compass and stand on this surface and see what direction that green line is pointing, that would be um, that would be what we call the strike. And the other thing that we need to know, so the strike would determine this direction, but um, we also have this angle, the angle that it's tilted at, which we call the dip. the dip is the maximum angle a surface makes with the horizontal. Measured downward. So this angle right there, that's the dip angle. And we will measure that different ways. We could, on this piece of paper or on this screen, you could measure that with a protractor. It's something like about a 30-degree angle. A little bit more space here. So the dip is always always measured perpendicular to strike. And in the vertical plane. So all that's saying is like there's a lot of different angles you could measure between this surface and that plane. If you could measure them at some odd angle, and you could get angles in there that are less than the dip. So we measure the dip perpendicular to strike. So you can see that here. So this is a 90-degree angle between the strike direction and the dip direction. So if we could mark, I'll just use a blue here. On the bedding plane, we could draw that's a 90-degree angle. And we should talk about the dip direction. So what is the dip direction? It's a direction the plane dips downward from the horizontal. And by direction, we mean compass direction. So on this diagram, we said it was 90 degrees. So like that direction I'm pointing there. So if the strike was north, the dip here is east. Let's color that arrow, call it dip direction. Okay, so the dip has both an angle and also a direction. So it's dipping. This one is dipping. Let's say we had our compass here, and that's the direction north. So the strike is north here. The dip is east. So these names, strike and dip, might be familiar from faults. If you've heard of strike-slip faults, like the San Andreas fault. So this is a fault where the direction of motion is parallel to the strike. So here we have a vertical fault, and the motion, you can see this block on the right has moved sort of into the screen. So the slip on this is parallel to strike, so we call it a strike-slip fault. And there's another kind of fault called a dip-slip fault. So if this block had moved downward instead of sideways, we would call that a dip-slip fault. So here we have another diagram. This is basically the diagram we tried to draw earlier, just slightly different orientation. So the beds here are dipping to the west now instead of to the east as we drew it. And they're showing, so in green we have these dipping sedimentary beds, and the imaginary horizontal surface, you could imagine the water level rising. Sea level rises up, and water is always going to make a horizontal surface on the top. So you can, if you ever kind of forget what strike is, you might be able to sort of imagine water coming up and how it will make a line. There'll be a line between the rock and the water. And if we were to measure the direction of that line here, it's exactly north again. We call that the strike. So we could actually, in our class, we could, there's different conventions, but we could also say the strike was south. And here we have again the direction of dip, which you can see is at a 90-degree angle. So if you were to slide down this slope, the steepest direction you could go would be at 90 degrees to the strike, and that's what we call the dip direction. So here the dip direction is exactly west, and it's dipping, and the dip angle is 30 degrees. So there's other ways you could go down the hill, at an angle like this. You would be walking down a 15-degree dip or some lesser dip. Later on, we'll talk about what's called a parent dip, which is if you measure at some other angle other than 90 to the strike, then you can get numbers that are less than 30 degrees. So we want to avoid doing that. I always use the true dip, 30 degrees.